Okay, so the lecture today is going to be on, it's a continuation of the lecture from last week. We are going to talk about Riemannian curvature tensor, and we are going to spend quite a bit of time computing some examples motivated by local computations, and then hopefully this will lead us into some other kinds of curvature, namely sectional curvature and Ricci curvature, which we'll talk about in the coming weeks. Okay. So that's the plan. We want to delve deeper into the notion of Riemannian curvature and do local computations. Okay? So I mean, just to emphasize, computations are essential and important because without these computations, locally or otherwise, there's not much meaning left in this course, at least for the curvature part. Okay? So let's start straight away. So we have seen some of the properties of the Riemannian curvature tensor last time. Remember, we talked about 4 properties and we express them as the symmetries of the tensor. So sometimes you can also call it the skew symmetries, but we'll broadly call it the symmetries of the tensor. And the Riemannian curvature tensor was essentially an object which takes 4 vector fields as inputs and outputs a scalar or a smooth function as its output, right? So it takes in the vector fields x, y as the input for r, and r of xy is now, r of xy is now going to act on a vector field. So if r of xy acts on z, that's a vector field, and then you pair that with a vector field w using the Riemannian metric. What you get is a function. Or point-wise, what you get is a scalar. So it had various properties. You can switch x and y, sign changes. You can switch z and w, the sign changes. You can transpose zw with xy, the sign doesn't change. And there was a fourth property called the Bianchi identity. Okay. So let's revisit these properties in local coordinates. So we are working in a patch, u comma phi, and the local coordinates for a point in u is given by x1 up to xn. So there's a manifold of dimension n. And in a local coordinate system, you always have coordinate vector fields, which I'll denote by del I. Del I is nothing but del by del xi. Right? The usual directional derivatives coming from the local coordinates. So we can introduce this new notation. So remember, you can calculate R of del I del j. What is R of del I del j? That is itself an operation which acts on a vector field and gives you a vector field. So R of del I del j acting on del k is going to be another vector field, correct? And because it's a vector field in this local patch, any vector field of this form can be expressed in terms of function combinations of d by dxj's or dj's. Okay, so I can express this left-hand side R of del I del j acting on del k as some coefficients times del r, where I've written this summation just for once so that it's clear that we're summing over R, and this right-hand side expression over here, as you can see, this is the Einstein summation convention. So the summation does not appear, but it means that if R appears both as a subscript and a superscript, then you sum over that. So this is implicitly a sum over R, okay? So these are the coefficients that appears when I express this vector field in terms of the coordinate vector fields. So I have called them R, I, J, K in the order that they appear here, and the superscript R matches up with the subscript R so that it's sum over R. So anyway, so these are some functions. You just call them R subscript I, J, K, superscript R. Okay. So there's a convention here. There's actually more than one ways to denote this object. Okay, so some people might use R, J, I, K, R here, or in some other way, but there's a convention. So you have to pick one. We're using the convention of Locarno. Okay. So because you might want to call this R, J, I, K, and R appears after K, but on the top and so on. So it depends on how you want to contract and sort of do things with indices. Anyway, so what we obtained, well, remember what is our Rijkl? If you recall from last time, Rijkl was nothing but R acting on del I del j, acting on the vector del k. So that is this, and then this inner product del L. So the entire left-hand side over here, right? This inner product del L. But that would mean this right-hand side inner product del L. But if I take the inner product of del R with del L, that's simply GRL. That's how the Riemannian metric is defined. So Rijkl is nothing but sum over R, these functions times GRL. Okay, where GRL is simply the inner product of del by del XR with del by del XL. So is this clear? I mean, this simple notational aspect. Okay. So these are really what one is going to be interested in the long run, and this quantity is nothing but these functions multiplied with GRL and summed over R. Okay. Which is again, I mean, see, GRL is nothing but this, and because the inner product is bilinear, you can move it around, and this is nothing but this. Okay, so whatever I just said, it's encapsulated by this one single line. So these numbers are the ones you're interested in, but these numbers are nothing but, if you go by this formula, you'll simply get this, and I'm denoting this by Rijkl. Are there any questions? Okay. All right. So, okay, fine. So you should remind yourself that these Rijkl, these are quantities that we had encountered earlier once, although in a slight disguise, that we did talk about Rij, and that turned out to be the Gaussian curvature when we're talking about surfaces embedded in R3. And that was the first lecture on Gaussian curvature from this point of view. So Rij with our choice was essentially up to a scaling the Gaussian curvature. Okay? So hence these quantities are going to be of importance. But let's look at the symmetries that we had last time in this local language. In this local coefficients, Rijkl is minus Rjikl. So if I switch I and j, the sign changes. That is because if I switch I and j, R of del I del j is minus R of del j del I, right? Because that's how the Riemann curvature is defined. It's nabla x, nabla y minus nabla y, nabla x minus nabla of bracket xy. So if I switch xy, the Riemann curvature changes. So that's okay. This was the first symmetry that we talked about. This was another symmetry that if I switch k and l to lk, there's a minus sign. Okay. There's another symmetry which was the last symmetry in our previous list, which is if I swap ij and kl pairwise, it becomes rklij and there's no change of signs. Okay. The fourth one is sort of what we spent a lot of time last time proving using Milner's octahedron, and this is the Bianchi identity, which says that if you keep the last entry L fixed, which means the last vector field del by del L is fixed, and then you're cyclically permuting I, j, and k, then you'll have three terms, you add them, that's zero. Okay? So I would like all of you to go back and look at those four equations that we had, and just see that those four equations immediately give you this locally, and this implies the other one, because you'll be computing things locally anyway. This is a tensor. So this is exactly the four properties that we had from last time. Okay. Are there any questions? So all these properties were proven last time. I'm just recasting them in local coordinates, in a local chart. Okay, so these Rijkl, you might think that, okay, so to understand the Riemann curvature, I need to know these, even at a point, I need to know this numbers, Rijkl. Well, you don't need n to the 4 many numbers, because a priori Ijkl, there are n to the 4 choices. I has n choices, j has n choices, and so on. But you don't need n to the 4 choices because of all these symmetries. So it will cut down the thing by quite a bit. Okay? And in fact, I'd given you an exercise last time saying that the curvature type quadrilinear forms, the space of such has a particular dimension, d square into d square minus 1 over 12. So if you have done that exercise, you'll realize how many free Rijks are there. The rest are determined by these symmetries. Okay, okay, so let's move on to some actual computations, if there are no questions. So as I indicated a few minutes back, if I take the Riemann curvature tensor for a surface and I calculate it, show that it's determined locally by R1212 up to a factor. So here when I say Riemann curvature tensor is determined by R1212, what I mean is it may not exactly equal R1212 because the coordinate vector fields that you have chosen may not be orthonormal. Okay, if it is orthonormal, then it turns out that this is exactly the Gaussian curvature. If it is not orthonormal, then you have to rescale this R1212 by a certain number. But you should remind yourself that for a surface, R1212 is only one of the few non-zero, potentially non-zero numbers, because whenever you're looking at R, I, J, K, L, I, J, K, and L can only vary from 1 through 2, correct? Because it's a two-dimensional manifold. And if you have three ones, for example, as I, J, and K, then R is 0, because you could have swapped any of the two, and then the only non-zero R, I, J, K, L is of the form there are two ones and then there are two twos, and the two ones cannot be in consecutive slots, and the two twos cannot be in the first two or the last two slots. So it could either be 1 2 1 2 or it could be 1 2 2 1. But 1 2 2 1 is negative of 1 2 1 2. Is that clear? Just by the last symmetry, right? So if I have R 1 2 2 1, if I switch the last two 1 to 1 2, I get a minus sign by the second equation, right? So for a Riemann surface, I mean for a surface, the only Riemannian curvature entry up to a sign is R1212, which may be 0, it may not be non-zero. Anywhere there's at least three ones or three twos in the indices, it's automatically 0. Is that okay? Okay, so this
Yes,
is,
sir.
yeah, so this is an important quantity. So up to a scalar, this is exactly Gaussian curvature, and we'll have a lot more to say about this later on regarding why Riemann defined curvature like this and what was his motivation and so on. But we'll get there. Okay? So yeah, so in particular, if del 1, del 2 forms an orthonormal basis at the point P or even over the chart, then this is the Gaussian curvature, and you have seen examples of this in not the previous talk, the talk before that. Okay? So yeah, so let me make a pedagogical remark. So you might ask, okay, we have these coefficients R, I, J, K, superscript R. These appeared when we were expanding the Riemann curvature, and whether you can express this in terms of the Christoffel symbols, because we know that the Christoffel symbols are themselves expressible in terms of the metric, because they are combinations of the metric entries and their partial derivatives. So if I can express these in terms of the Christoffel symbols, then in turn we would know that these coefficients can be expressed in terms of the metric alone, which in particular says that the Riemann curvature can be expressed entirely in terms of the metric, correct? So it turns out that you can. So let's see how to do this. Well, remember, what is the definition of R del I del J acting on del K? It is nabla del J, nabla del I acting on del K, minus nabla del I, nabla del J acting on del K, minus nabla of the Lie bracket del I del J. Del I del J are coordinate vector fields, so the Lie bracket is 0. So that term vanishes. So typically you'll have three terms, right? But that term is not there, so we only have these two terms. But now you can use the Christoffel symbols, because that's precisely what happens, right? So whenever you encounter covariant derivative of del K along del I, you're going to get these Christoffel symbols appear. Again, this is a sum over L, and I'm using the Einstein summation to save myself from writing summations over and over again. When you read this, you have to either get used to the Einstein summation convention and use it perfectly. If you're not used to that, make a mental note that there's a summation here, and then use the summation as most mathematicians would do. And so my point is, stick to one convention when you're solving problems or writing things down. Okay? But I'm going to use the Einstein summation convention. So the next one is nabla del K along del J. That's going to be gamma LJK times del L. And this is again a sum over L. Okay. Okay. So you can just compute, and it's just a couple of lines of direct computation. What you'll obtain is that these coefficients R, I, J, K superscript S looks like this. So there will be some partials of the Christoffel symbols and some products of the Christoffel symbols. Okay? So this looks not as nice as some of the earlier formulas, and it is, I mean, it cannot be simplified any further. And there's an Einstein summation here in the last two terms, sum over L, sum over L. Okay. So this is a rather ungainly formula, and we are not going to make much use of it. But as I said, this is just for your own edification, that in case you wanted to ask this question, the answer is yes. The Riemann curvature can be expressed entirely in terms of metric, but now that it involves the first derivative of the Christoffel symbol, that in particular means that you're involving second derivatives of the Riemannian metric, because the Christoffel symbols already involve one derivative of the metric, right? So the Riemann curvature is a second derivative, is a quantity involving first and second derivatives of the Riemannian metric. Okay, but we'll not make much use of this formula in the subsequent lectures. This is just, but some of you might find this useful in some other things that you might study later on. So, okay, so let's, having mentioned this formula, let's move on to something which is of more relevance for us. So the first exercise for you, and this is probably something that you should do just to sort of satisfy your own conscience, is that Rijkl is identically 0 for Rn with the Euclidean metric. So remember, the Euclidean metric is the Euclidean metric coming from Rn as a metric space, and I am using that also as a Riemannian metric on the Riemannian manifold Rn. So in either case, you can show that Rijkl is 0. That either follows from the previous formula, because the Christoffel symbols are 0, so when you differentiate and multiply that 0, or it follows directly by calculating the Riemann curvature tensor. Okay? But either way, you should know that, you should know how to show that this is 0. So we call a Riemannian manifold, meaning it's a smooth manifold M with a Riemannian metric G. We call a Riemannian manifold flat if the Riemannian curvature tensor vanishes, which means R as a tensor acting on 4 input vector fields should always give me 0. Okay? But that is equivalent to computing this thing locally, and when you compute things locally, that is equivalent to showing that Rijkl is 0. That means R of del I del j acting on del k dot product del L is 0. Okay, so that's the definition of a manifold being flat. We will later see a slightly different definition of a manifold being flat, and it will turn out that they are equivalent, but let's go with this definition because this is obviously motivated for I mean, reasons that are clear. So Rn is a flat manifold. Okay? So flatness has everything to do with the metric. It has nothing to do with the underlying topological space. Rn, if I change the metric to something else, could very well end up being a non-flat manifold. It could very well end up having curvature. Okay? So flatness is a property of the metric and not a property of the topology, obviously. Okay, so let's take an example, and this is an example we partly worked out in one of the earlier sections. It's an example on covering maps. Okay, so let pi be a Riemannian covering map. So forget the word Riemannian, it's a covering map. So m tilde and m are smooth manifolds, and pi is a smooth map. Between these manifolds, it's also a covering map. That's what a covering.
Sir?
Yes.
Sir, isn't there another definition of flatness that every point has a neighborhood which is isometric to Euclidean?
Well, yeah. So we'll get there. So that is one of the claims that we're going to make. Okay. But
so
yes,
they're equivalent.
yeah, they are. But the thing is, see, you could have defined it that way. But the point is, I'm sort of defining it this way because you might say that what happens to Rn and then these Rijkl, the way I've defined last time, is Riemann curvature is measuring how far the manifold deviates as a Riemannian manifold from Rn with the standard metric. That's what this R is measuring, right? So in some sense, if you think Rn is flat and Rijkl is 0, then you declare anything with the same property to be flat just based on this motivation. So yeah, so that is one definition. There's another definition using sectional curvature, but that will come much later, maybe next week. But they're all equivalent, as it turns out. Okay? So, all right. Any other questions?
Yes, sir.
Okay. So yeah, so this pi is a covering map, meaning it's a map of smooth manifolds and it's a covering map. And being a Riemannian covering map means that m tilde and m have Riemannian metrics assigned to them, and this map is a local isometry. Okay, so not only is the covering map a local homeomorphism, but it's a local isometry. So, and we have seen plenty of examples where this actually happens. Okay, so I mean, we'll discuss quite a few, but you already know of an example. So can anybody think and give me an example of a covering map which is a Riemannian covering map in this sense, that it's a local
R to S1,
R to S1,
R to S1.
R with the standard metric and S1 with the with the usual
Yeah.
detail. So R to
Yes.
S1 is a local isometry. It is obviously a covering map, and there are plenty of other examples. Okay, as we'll see. So like Sn mapping to Rpn through the antipodal map. If you define the metrics appropriately, it will be a covering map. So that is usually what people do. You start with a covering map, you put a metric somewhere, and then you pull back the metric or push forward the metric so that the underlying metric is a local isometry, and hence you make it a Riemannian covering. That is a useful tool of the trade, so to speak. Okay? Anyway, so that's what local isometry is. So if you have, but in our case, we are not interested in constructing such. We are given such a covering map. So if you choose local coordinates for M and local coordinates x tildes for M tilde at points P tilde and P, by choice, we want pi of P tilde to be P, which means P tilde is one of the inverse images of P. And the local coordinates x1 tilde up to xn tildes around P tilde when I project down gives me the local coordinates at P, which are the corresponding x1 up to xn. Okay? So you can show, again, essentially because it's a local isometry, and I would highly encourage all of you to go back and do this exercise. It doesn't take much work. It's a couple of lines, but show that the Riemann curvature at the point P tilde associated to the vector fields del I tilde, del J tilde, del K tilde, del L tilde. So recall this notation. This notation means what? It means you calculate the Riemann curvature of del I tilde, del J tilde acting on del K tilde, dot product, del L tilde with respect to the metric G tilde. That's what the left hand side here means, right? The right hand side means the same thing but happening around P in M. And just to be sure that you're following, del I tilde simply refers to del by del x I tilde. So the coordinate vector fields for the coordinates x tildes. Okay. So yeah, so this is not unexpected. You can show that the Riemann curvature R ijkl tilde and R ijkl are the same. Okay. But that is expected because we know that pi is a local isometry, and local isometries are going to preserve these curvatures. The curvatures are essentially coming from the metric distance function, and local isometry means the distance function.
So basically, any Riemannian manifold which can be covered by some Rn is flat.
No, it can be covered by some Rn, but it has to be covered in this Riemannian sense.
Yeah, I mean in the Riemannian sense.
Yeah, so the point, but the issue is that if you put Rn with the standard Euclidean metric on Rn, and then you ask whether the manifold downstairs has an induced metric, the induced metric downstairs is going to be typically very special. I mean, you're right.
Sir, can you repeat what you said?
I'm saying what you said is correct, but the point is that when you say it's a Riemannian covering map, that means you're already thinking of Rn with the Euclidean metric as the top M tilde G tilde, and you have a M comma G downstairs, right? So the point is that when you have M comma G downstairs, this G cannot be arbitrary. This G has to be somewhat very special, that it has to come from the fact that it has to be some sort of a push forward, or at least locally identifiable with the standard metric of Rn onto a local piece of M. So you're right. I mean, if you can cover M by Rn with the Euclidean metric, and then that induces a compatible metric on M, then M is going to be flat. Yes. By this exercise, for example. Okay. So, any other questions?
Sir, can you give example of any other metric on Rn which is flat, apart from this Euclidean metric?
No. So that's the thing, right? So we'll see how to geometrically extract what flatness means. So this is really an algebraic sort of characterization, in a sense of flatness. So there are other characterizations, and one aspect is going to be, if you say that a manifold is flat, then you can show that it's locally isometric to Rn, but you cannot claim that it's globally isometric to Rn, and we'll see examples of that. Okay? So
So
there are
locally isometric to Rn in Euclidean, what the Rn metric is Euclidean, right?
yes, it's locally isometric to Rn as a Riemannian manifold with the Euclidean metric, but not globally. And we'll see examples of that. Okay, so does that help?
Yes, sir.
Okay, so we'll go through several examples. So this is just the beginning. So this is a computational definition of flatness. If you want to understand more, then just hold your patience for a bit. We'll get there. Okay, we'll see a characterization using parallel transport, for example. So, okay. So I want to talk about a particular example because this is an example all of you have seen in the algebraic topology course. This is the first instance of a non-trivial covering that one sees. The map from R to S1, which we just talked about, sending S to e to the 2 pi I S. That is a Riemannian covering. And I'm taking two copies of that and taking the product. So this is a map from R cross R to S1 cross S1. And this basically sends s comma t to exponential 2 pi I s exponential 2 pi I t. Okay, so I'm sure all of you should be comfortable proving that this is a covering, and in fact this is the universal cover of s1 cross s1, which is abstractly a torus. Okay, so here I want to induce a metric on S1 cross S1 by using the metric on R cross R. R cross R has the obvious Euclidean metric, and I know R cross R is flat because of the first exercise on this slide. So I want to use the metric on R2 to define a metric on the torus. So if you remember, how should the torus in this case look like? Well, if you look at R cross R on the plane, there's a unit square, and the unit square is the fundamental domain which generates the torus, because you identify the two horizontal sides of the unit square and the two vertical sides, and if you close them up, that gives you a torus, right? And if I translate left or right, up or down by any integer of this unit square, it will give me another copy of the same torus, right? Because when I exponentiate, whether it's e to the 2 pi I s or e to the 2 pi I s plus an integer, it doesn't matter. It's still e to the 2 pi I s. So that basic unit square 0, 1 cross 0, 1 in R2, when I identify, that's going to give me the torus. That's what the covering does, right? Okay. So the metric that you have on R2, that is invariant under any translation, up, down, right, left, diagonal, because the metric is the constant metric, the standard inner product at every point. So since the metric on R2 is invariant under translations, you can induce a metric on S1 cross S1, because you can think of S1 cross S1 as identifying the two horizontal sides of the unit square and the two vertical sides, and there's a well-defined metric on this, okay? Because the metric everywhere is the same. And it's clear from the exercise that the previous exercise, not this one, that this torus is going to be flat because this is covered as a Riemannian covering by R2, and R2 is flat. So this torus is flat. Okay, it's going to have no curvature, and you can check that it's a Riemannian covering. That's essentially how the metric on S1 cross S1 is constructed. So the only thing is on the 0, 1 cross 0 on interior, there's a well-defined Riemannian metric. When you identify the two vertical sides, you have to say whether the metric is the same. Well, the metric is the same because the metric on R2 is the same at every point, because it's the constant matrix 1001, right? So, okay. So for this torus, which comes as the quotient of the plane by z cross z, which is the first z for the translations right or left, the second z for the translations up and down. If you take the quotient, you basically get a square, identify the sides of the square, so that manifold will be flat if it has the metric induced from the plane. Is that okay? So all of what I just said is not very complicated. You just have to ensure that you understand that there is an induced metric on S1 cross S1, and when you just have to write it down. Once you write it down, it's clear that the metric exists essentially for free. Okay. Okay, so this is a flat torus. You shouldn't confuse this flat torus with the usual picture of the torus that we draw, and we often like to draw this as our torus. And it's a very nice picture. Unfortunately, this is a picture which embeds the abstract torus inside R3. The abstract torus doesn't live in R3. It's just in an abstract space. It's a product of two abstract S1s, right? So this is an embedding of the topological torus inside R3, but this torus is not flat. And for those of you who recall having computed the Gaussian curvature for this torus in the course on curves and surfaces, you would have realized that the curvature on this part of the segment was positive, the curvature on this part was negative, the curvature on the top along certain lines was zero. So it had variable curvatures along this torus. This torus was definitely not flat because the Gaussian curvature was not constant. Okay. So this is not the flat torus. The flat torus that we talked about is an abstract one coming from the quotient of the plane. Okay. I mean, quotient of the plane in a Riemannian sense, not in a topological sense. So yeah, so the standard model, like the one above that we usually like to draw, is not flat. Okay? So just keep that distinction in mind. Topologically, they are the same. They're homeomorphic, they're diffeomorphic, but they're not isometric as Riemannian manifolds. Okay? Is this example of, all right? Any questions? Okay, so we'll encounter this torus once more later on in the talk. So just keep this picture in mind. So the lines are not very important here. The lines are just meridians and longitudes, but the lines will be important for the next, the next time the torus makes an appearance. Okay. Okay, so now let me come to a more geometric way of describing flatness by bringing into the picture parallel transport. And when I discuss this example, there will be two subsequent follow-up examples where there will be lots of pictures, but the idea is that you should go back and solve analytically what those pictures mean and know how to do them. Okay? But let's write it down. So this is actually inspired by a problem from Docarmo. So you start with the manifold M with a metric G. So it's a Riemannian manifold. It has a crucial property. What's that property? The property is this. Choose any 2 points P, Q in M, and you choose a curve from P to Q. Once you have chosen a smooth curve, we have seen that you can, so once you have a Riemannian metric G, you have a connection nabla, the Levi-Cevira connection. Once you have a connection, you can talk about parallel transports, right? So parallel transport means given a vector, you want to solve the equation nabla gamma dot x is equal to 0, where x at gamma 0 is a given vector v. So that the vector field x has to be parallel to gamma. And this has a solution, the unique solution once you prescribe the initial data, and this x is called the parallel transport. So x of gamma 0 is v, and x of gamma 1 is going to be whatever the output is. And that's going to give you a map from the tangent space at P to the tangent space at Q. But this will depend on the curve gamma, typically. So the crucial property is that you choose 2 points, choose any path joining P to Q, parallel transport a vector at P along this path to the corresponding vector at Q. The property is that this parallel transport is independent of the path joining P to Q, which means this linear map that you get from TPM to TQM is independent of the curve gamma. That's the property that the manifold possesses. Okay. So if that happens, what's the conclusion? Let's see what we can conclude. So is the statement clear what the property is? So we'll see a few examples where this is not true, and in general this is not going to be true, because as expected, if I take a vector and parallel transport along a curve, the output will typically depend on the curve that I've chosen. It will simply not be generically independent of the path. Okay? So this is somewhat stronger. It's saying that this property is true. So we are going to claim that if this property is true, then the manifold is flat. Okay, so that's what you're going to claim. So, I mean, this So that's the first claim. Okay, so I haven't written it down. I should have. So the claim is M is flat. So let's see how to prove that. So to prove that M is flat, what do you have to show? You have to show that Rijkl is 0, right? But it suffices to show that Rijk, I mean R of del I del j acting on del k, this is 0, right? Because when you get Rijkl, you're basically taking R del I del j acting on del k dotted with something. But if this vector itself is 0, then dotting with anything is 0. So that's what we're going to show. We're going to show that R of x, y acting on z is 0 for any three vectors x, y, and z at P. Okay. So that's the claim. So let's first get into the middle of the proof. So let's consider a smooth map from U to M. What is U? U is going to be an open box, slightly more than length 1 on both sides. So it's minus epsilon to 1 plus epsilon cross minus epsilon to 1 plus epsilon. So instead of 0, 1 cross 0, 1, it has a thickening of epsilon on all the sides. Okay. So this map has a property that f of s comma 0 is constant and it's f of 0, 0, right? So if you look at the line y equal to 0 in this box, all of that line is mapped to a constant, namely the image of f 0, 0. Okay. So we'll call such a map a parametrized surface. This is just a nomenclature. I'm not saying that this is an embedded surface. It's clearly not an embedded surface because the first condition f of s0 is f0, 0 already tells you f is not injective. So this is called a parametrized surface because it's a map of an open square inside M, and the open square, when it maps into M, has a parameterization in terms of two coordinates s and t, or u and v. So that's all. So are we okay with the setup so far? Okay, so let's take v0 to be an arbitrary tangent vector in M at the point f00. So consider the tangent space T of f00M, choose a vector there v0, and we are now going to define a vector field v along f, meaning what? We're going to define a vector field v on the image of f. So the image of f is going to be some sort of a surface, may not be embedded, and we want to define a vector field along that surface. Okay. So how should we define this? Remember, what is the image of f? The image of f is the image of a square, right? And the square has this special property that the y-axis gets mapped to a point, single point under f. And if I stay on a particular point on the y-axis, say at s comma 0, I can just look at the vertical line moving all the way up. So from s comma 0, I can move vertically up or down, and that gives me a vertical slice. Same for any point of the form s comma 0. I just stay at the line y equal to 0, and then I move up. And if I take these vertical line segments, the union is the whole square. Right? So I'm going to define a vector field, which is simply take v0 and parallel transport v0 along the curve f of s dot. Okay, so the point is s is fixed, and you define the vector field v at the point f of st to be the parallel transport of this fixed vector v0 vertically up. So vertically up in the u in this box, but that means moving vertically up in its image in M. Okay? So you'll see a picture soon enough. So let me just show you a picture. Okay? So there's the picture. Okay. So if you, so I'll go back to the previous slide. Let me just show you the picture and then we'll go back. So this is, so can everybody see this picture? So this is the box. This is the map F. It has the property that this line s comma 0, this x-axis, gets mapped to this red dot, one single point, which is f of 0, 0. We start with the vector v0 at the tangent space. So this v0 is not necessarily a vector on the surface colored by green. It's just a tangent vector inside the big manifold M. And what I do is I parallel transport this v0 along these vertical blue lines. So if I'm here at the point s comma 0, I move up by this vertical line. That vertical line corresponds to a curve on the surface here. I parallel transport this v0 along this blue line. What I get is vs1, okay, because I stop at time 1. I could do the same thing along this blue line, right? Which means I take this V0 and then I parallel transport along the image of that blue line, the leftmost blue line, and that's going to end at F01. So what I get is V01. So V01 is going to be a tangent vector at TF01 of M. And so on for all the other points. If I want to go to assign a tangent vector at any point here, I simply start at the corresponding S comma 0, go up. That would mean I start here, parallel transport V0 along the corresponding image of the vertical line segment under F. So is the definition of V clear? How I'm defining V? I'm defining V on this whole image of F by simply looking at a point S comma T, looking at the corresponding point S comma T in the U, and then taking the line segment joining S0 to ST, looking at its image, parallel transporting V0 from F of 0, 0 to F of, F of S0 to F of ST. That's all. Okay. So I have a vector at every point F of S comma T, which I'm denoting by V of S comma T. So is it okay? I could repeat this.
Yes, sir.
There. Okay. So let's go back to. So I didn't want to have the pictures in both places because it's just a waste of a slide. So the point is that this is how V is defined. You parallel transport V0 along the image of a vertical line segment, and V of ST is now a vector at T of FST of M. So the first exercise for you is to show using smoothness of parallel transport and so on that V is a smooth vector field on F of U. Okay. Okay, so now what do we want to do? Well, we want to obviously compute certain things about curvature. So there are two coordinate vector fields on U, del by del S, del by del T, right? So I can take their images under df, and that's going to give me two vector fields, del by del S acted on by df and del by del T acted on by df. I'll call them del S, del T, subscript. So just make sure that you're not confusing both of them. So del by del S, del by del T are the coordinate vector fields on U. When you linearize the map F and apply to the coordinate vector fields, what we get are vector fields on F of U, and I'm calling them del S, del T. Okay? So by construction, we know that, so let's look at this, the first equality. By construction, the covariant derivative of V along del T is 0. So why is that? Well, that is because we define V simply by parallel transporting in the T direction, starting at V0. And when I calculate the covariant derivative of V along del T, this is going to be 0 because V is the parallel transport of V0 along the integral curves of the vector field del T, right? Because the integral curves of the vector field del T are precisely these curves, f of s comma dot. So by construction, this first equality holds. I'll pause here for a moment and just let people think through this. So there's nothing very hard going on. This is true basically by construction because V is by construction a vector field parallel to del T. Just make sure you understand that. Is this okay with everyone? Okay, so that's essentially how we have constructed V. It is by parallel transport. What about del S, del T being 0? Well, that is because these are images of coordinate vector fields, and coordinate vector fields are 0 under the Lie bracket. So you basically have to show that df of the Lie bracket. Anyway, I mean, so the thing is, these are going to be coordinate vector fields in the corresponding f of u. So this is 0. Okay. So because this is like df of something, comma df of something, but that simply becomes df of the Lie bracket of del by del s with del by del t, but the Lie bracket of del by del s and del by del t is 0, so df of that is 0. So what we know? Well, we know that the Riemann curvature tensor is defined in terms of 3 terms. So if I want to calculate r of del t del s, that's going to be what? That's going to be nabla del t del s. See, r of del t del s is going to be nabla del s del t minus nabla del t del s minus nabla of the Lie bracket. That term vanishes. But I'm not saying that 0 is equal, there's an equal sign here. So when you read this, you have to be careful. So let's look at the first equality. Why is the first equality true? The first equality is true because nabla in the direction of del S is acting on something which is automatically 0 because of the first equality here. So this is 0, right? Because it's nabla del S of 0, so that's 0. So once this is 0, what do you get? You get that you get that R of del T. So if you want to calculate the Riemann curvature tensor, what should you get? See, the Riemann curvature tensor is what? The Riemann curvature tensor R del T del S is del S nabla del S del T minus nabla del T del S, right? Acting on V. So if I ignore this 0 part, so ignore the 0 for now. If I look at A is equal to B, that's precisely the definition of the Riemann curvature tensor, right? Just ignore the first 0. But now I'm saying that the first term is equal to 0, hence the last two terms add up to 0. Is that okay? It's written in a slightly non-natural way, but it is correct the way it's written. Are there any comments or questions? Anything that you did not follow? Okay, so what we have here is that the Riemann curvature R del T del S acting on V plus this quantity is 0. Right? So somehow if you can show that this quantity, this nabla del T, nabla del S acting on V is 0, then we would be in very good shape because then you would conclude that the Riemann curvature del T del S acting on V is 0. And because V was arbitrary and del S del T can be chosen, because F can be chosen appropriately, we'll see that R of XYZ is going to be 0. That's going to be the punchline. So our next claim is to show that nabla del S V is 0. Okay. So now let me give you the picture. So there's the picture that we had. So now let's consider two curves joining f of 0, 1 to f of S1. So here's 0, 1, here's S1. Their images, this is f of 0, 1, this is f of S1. And so there are two obvious curves joining this point to this point. One is this curve in dark red. That's simply the image of the horizontal line, right? There is another curve which is the blue, the concatenation of the three blue line segments. You go down, you go to the right, and then you go up, correct? So in the picture that should correspond to going down all the way using this blue. Remember that all of this line x-axis maps to a constant. So this horizontal blue segment will map to this point only, and then it moves up through the other blue line to f of 0, 1. So these are the two obvious curves joining f01 to f of S1. Is it clear? Okay. So now we can use the property which we haven't used so far. The property says that if you parallel transport a vector from P to Q, the parallel transport does not depend on the curve chosen. Which means what? Which means we could have chosen V01 and parallel transported that along this deep red curve. We might have gotten something else. We may not have gotten VS1, right? But we can take V01, parallel transport it back by the blue curve. What do we get? So if you have followed this so far, you should be able to think and answer this question. So remember how VS1 was constructed or how VST was constructed. So my question is, if I start with V01, parallel transport backwards by this blue curve and get to the point F00, what should be the output?
V0.
It's V0. So
V0.
Just by, yeah, it's by V0, it's by definition, because V01 was the parallel transport of V0 along the opposite curve. So if I parallel transport V01 backwards, I get V0. This horizontal line segment is constant, so V0 stays V0. And then when I parallel transport V0 by this blue curve, I get VS1. Correct? So because the parallel transport is independent of the curve, this also means that if I take V01 and parallel transport along this deep red curve, it's also going to be VS1 because it's independent of the curve. That's a crucial property. Okay. But what is this deep red curve? This is the integral curve for the d by ds flow, right? Because these are the horizontal lines which are the integral curves for the del by del s. So that basically tells you that if I take Vs1, if I take this vector field along this red curve, and if I covariantly differentiate along del by del s, I'm going to get 0, because V is also a parallel transport along del by del s because of the invariance of which curve you choose. So is that okay with everyone? So this is a very nice, it's a very nice argument that you somehow use this abstract property to show that a parallel transport defined one way is also a parallel transport defined another way. Okay. So that's the point. The point is that if I covariantly differentiate V along del by del S, yeah. So Vs1 is the parallel transport of V01. So this implies that if I calculate nabla of del S of the vector field V at f of S1, it's going to be 0. Okay, because V is parallel to del by del S. So once this is 0, I can apply nabla del t, that's going to be 0. But that at the end of the day is going to tell me that R at the point f of 0, 1, del t del S acting on the vector V is 0. Okay. So we're almost there. So this is saying that if I can arbitrarily choose my f so that del by del t is whatever I want, del by del s is whatever I want, and f of 0, 1 is an arbitrary point p, and v0 was arbitrary to begin with, then this tells me that R of x, y, z is 0 for any x, y, z at tpm. Correct? So given p and vectors xp, yp, zp, I want to construct an f such that f of 0, 1 is p, del by del t at p is yp, del by del s at p is xp, and your v at f01 is going to be zp. So if I can construct such an f for any choice of xp, yp, and zp, I'm done. Because that tells me that R at p of xp, yp, zp is 0, but that means the Riemann curvature itself is 0, because x, y, z was arbitrary and p was arbitrary. So let me complete the proof and then I'll mention the exercise. So since everything was arbitrary, we conclude that the Riemannian curvature tensor is identically 0. So the only exercise here is that you have to show that such an f exists. And this is just a local exercise using exponential at p. And I mean, it's good if you try to do this and you see whether you understand the nuances of the exponential map, because that will tell you that you can always make this choice. It's a local chart. So, I mean, the box can be as small as you want. You just need some small box where this can happen. It doesn't have to be of length 1 cross 1. Okay? So that's the proof. So if you know that the parallel transport is independent of the curve, then the Riemann curvature vanishes. Are there any comments or questions or doubts regarding this example? Okay. Yes. Any questions?
Sir, can you explain why nabla del S V at fs, 1 is 0 again?
Yeah, so I see when you say, so I think somebody's microphone is, yeah. So when you, so forget evaluation at fs1. If you say that nabla of gamma dot x is 0, that means what? By definition, that means, I mean, by definition, that means whatever it means, you have to compute. But we know that that also means that the vector field x is parallel to the vector field generated by gamma dot, right? That is one way of interpreting. I mean, that is the definition of a vector field being parallel. So here I'm saying that if you look at V, if you go back, let me go back one more slide. So you look at this V, right? So this V is defined by starting with V0 and then parallel transporting along these vertical blue lines, right? Because all of this x-axis goes to a point. So you have these blue lines going up, take their images, and that determines these VSTs. But because of the independence of the path, if I parallel transport this V01 along the red curve, that is equivalent to parallel transporting this V01 along the blue curve, down and then up, right? But if I parallel transport V01 down by the blue curve, I get to V0. And then when I parallel transport V0 back to here, I get VS1. Because that is how I define my V. Because of the independence of the path, that means if I parallel transport V01 along this dark red curve, I get exactly VS1. And that is true for any S in the middle. I mean, I could have gone down here and then chosen an S prime and then taken the blue curve at S prime comma 0. I would have come back at B S prime 1. So what I'm saying is this V as defined along this deep red curve is parallel to the vector field del by del S, which is really this vector field here, and its image under del F is this vector field del S. And this red curve is simply an integral curve for the vector field del S. But what we have just shown is that the V is parallel to del S. But once V is parallel to del S, this quantity is going to be 0, right? This quantity. So I'm just evaluating this at f of s comma 1. You could evaluate this at any other intermediate point. Okay. Is that okay?
Yes, sir.
So yeah, so it's I mean, this independence of the path is very crucial, because then it gives you the other covariant derivative is 0, and then in the Riemann curvature there's nothing left. The Lie bracket is 0 because it's coordinate vector fields. Both the nabla del S, nabla del T are 0, so the Riemann curvature basically becomes 0. And then the exercise for you is to show that locally you can always choose an F which makes these arbitrary choices possible. So R, YP, XP, ZP is 0, but since P was arbitrary, X, Y, Z were arbitrary, the Riemann curvature vanishes. Okay. So good. So any other questions? Okay. So this is an abstract sort of characterization. It says if parallel transport is independent of the path, then curvature is 0. So before we do some examples, can you think of an example where this property is true? So what's the first example that can come to your mind where the property
Sir,
is true?
Rn.
Rn, yeah. So in Rn, parallel transporting a vector means it's the same vector everywhere. It doesn't matter which curve you choose, right? That's exactly the parallel transport, because parallel transport is covariant derivative, and nabla x acting on y is going to be dx, the usual thing, dy acting on x. So if you keep the same y, then dy is 0, so dy on x is vacuously 0. So on Rn, parallel transporting a vector is the constant vector field, right? So, but in Rn, we already knew that the Riemann curvature is 0. So it's very natural to ask whether this is if and only if somehow I told you that the Riemann curvature tensor is 0, does it mean that the parallel transport from P to Q is globally independent of the path? We'll come back to this question. Think about it. I mean, some of you might have strong inklings or gut feeling one way or another. You might think that it's true. You might think maybe it's not true or whatever. But it's a delicate question. We'll come back to this maybe in the next talk. But however, we will talk about some related converse statements in today's lecture. Okay. So, okay, good. So what we infer from the previous example is that for manifolds which are not flat, you do expect to choose points PQ, and you do expect to see that the path you choose between the 2 points determine how non-trivial the parallel transport is. I mean, you do expect to see that, because if no 2 points have this property that any 2 paths will give you the same parallel transport, then the manifold would have been flat by the proposition, which means a non-flat manifold must fail to exhibit this property. Okay. So let's take the torus. Of course, we are not going to take the flat torus, simply because we cannot draw the flat torus in R3. The one we can draw in R3 is non-flat, so let's draw that. So consider parallel transporting V0 along the closed loop. So this is my torus. Okay, I've already given the exercise earlier. So, but as we move through the slides, you'll see what the exercise is. Okay. So recall the curve, the parallel transport is happening to this vector V0. This vector is being parallel transported along this black curve. I hope all of you can see this black curve. So it basically goes up by an angle of 90. So if you think of this in terms of 2 angles, theta and pi, this constitutes an angle 90. So if you go along the blue circle, this black piece is a quarter of the blue circle. Okay, so you go 90 degrees, I mean pi by 2 up along the blue circle, and then you go pi by 2 along the red circle, because if you see, the red circle itself has 2 pi, and this is 1/4 of that. The other quarter is here, the other quarter is here, and that's so you go pi over 2 along blue, pi over 2 along red, pi over 2 back along blue, pi over 2 back along red. So it gives you some sort of a deformed rectangle. Okay. In fact, in the usual chart, this is going to be a rectangle, but on the torus, it looks like a curved rectangle. So this is my loop. So instead of doing it for P to Q, I'm just choosing Q to be equal to P, in which case our claim would be that there is a loop, so that when I parallel transport along a loop, the parallel transport is not identity. It's something non-trivial, correct? Because there's a constant loop at P, the parallel transport there is identity, and there are lots of non-constant loops at P. So that's the setting. So this is my loop, and what is my V0? My V0 is a tangent vector of the torus, and this is a tangent vector in the direction of this black curve here, like the equatorial black curve. So this is a V0, which is a tangent vector to the torus. Okay, is the setup clear? So now we're going to parallel transport this by going up, going to the right, coming down, going left. Okay, so let's see what happens. So remember, when I parallel transport this, here what would happen is, so I'm not parallel transporting this as a curve in R3, because if it was in R3, it would be somewhat different. So this is happening on the manifold, the torus. If I parallel transport this curve, it will still remain tangent to the surface, but it will end up being this curve. So this is again tangent to the top black curve. Okay. So now if I parallel transport this curve along the top black curve, what do you think would happen? Will it start turning as the black curve turns, or it will stay the same? Remember, I mean, how was the connection on the torus defined? This is a torus inside R3. The connection is defined by taking the usual connection on R3 and projecting it to the tangent space. So for the first parallel transport, we didn't do anything. You just think of this black curve as a curve in R3, and parallel transporting V0 in R3 would mean you keep the same V0 everywhere. But that's literally what we did. We kept the same V0 along this curve, and it happened that it was along a meridian, so all these were tangent to the surface. So when you project, you don't lose anything. Okay. However, if you do the same thing here, you would be saying, okay, I just sort of, here I could do the same thing. I could take this vector, and then I can keep taking copies of that along this black curve. Will it stay tangent to the surface? That's the question that.
No, sir.
No.
No.
Really? See, this red curve, this is, if you think of this torus, this black curve is the topmost, is part of the topmost red circle, right? So what is the tangent space to any point on the topmost red circle? What does the tangent space look like? See, if you put a piece of paper on this torus, it will rest exactly on this red circle, of which the black circle is a part, right? There's one red circle like that below, there's one red circle like that on the top. So for any point on this red circle, I hope this red circle is clear, right? This topmost red circle in terms of height, what is the tangent space at any point? It is a parallel.
Is the plane containing the circle?
Yes. So what is that plane? Is it parallel to XY plane?
Yes.
Yeah, it is parallel to XY plane, right? Because if you really take a donut and if somebody serves you, then there's exactly a circle of contact of the donut on the piece of tray where it's served, and this is the top circle of contact. So any point on this circle is going to have the tangent space which is parallel to the XY plane, correct? And this red vector is also a vector on that plane. So if I just literally transport this vector as I would do in R3, it would still stay on that plane because it's still parallel to XY plane, right? So the literal, so if I literally parallel transport this, pretending this is happening in R3, if I project it back, I don't lose anything. I get the same thing back because it's already on the plane. Okay? So when I parallel transport this, what I get is this. You just have to mentally imagine if you have a torus or something like that in front of you, it will be the same vector. But the point is when it goes here, this vector is now going to get aligned with this blue curve. So this is still a horizontal vector, but it's now aligned along with this 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 black line because I have rotated this by 90 degrees. Okay. So these are all horizontal vectors. Okay, it's hard for me to draw a sheet of paper where these vectors lie. This is literally the same vector moved over. And when I project it onto the tangent space, I don't lose anything. Okay, so any questions so far? So all of this is something that you have to write down the equation of the loop, write down the parallel transport, and then solve. But you know what to solve because you already have a guess for the answer. So that's what the exercise says. So if I
So, sir, the black lines which are parallel to the xy plane, the bottom line and the top line, they each subtend angle of 90 degrees, right?
no. Yes, they each subtend an angle of 90 degrees. Yes, that's true. So
Okay.
yes, all of them. So see, this is literally like 19. So if you think of the torus in terms of polar coordinates, this is 19, 90, 90, 90. Yeah, hence this matches up exactly with the way the black curve is pointing. Otherwise, it would be a different deficit. Yes. So you
Okay.
start off at this point, you go up by 90 along the meridian direction, you go 90 along the red direction, and then you come back 90 along the blue, and then you come back 90 along the red. So this is not 90 in the internal angle setting, but 90 in the polar parametrization of the torus, because the torus is parameterized by two angles, right? Theta and pi.
Okay.
So it's 19 theta,
Okay.
19 psi, and then minus 19 theta, minus 19 psi. Is that yes? That's a curve. I didn't write it down, but that's what I meant. Okay.
Okay.
Yeah. So now, if you
Okay.
parallel transport this curve, what will happen? Well, you'll get this because now the point is this black curve is a geodesic. I mean, you can use that fact or not use that fact, but the point is once it's a geodesic, the velocity is going to be its parallel transport. So if you end up here, it's simply going to point down, because the tangent space at this point is a plane which is a vertical plane, right? It's just touching the torus at this point. So this is a thing which it doesn't look down, but it should really look pointing down. Okay. So now if I parallel transport this vector along this last black segment, what should I get? This is the same question. If I look at any point on this last black arc, the tangent plane looks like a vertical plane, right? Just that the vertical plane is turning as the point moves. But it has a z axis in it. So if I take these vectors, I simply just take the usual parallel transport in R3. They're all going to be tangent vectors because they're all going to lie in the corresponding tangent plane. So the projection doesn't lose anything. Okay. Is it all right? So the exercise that I have for you is that, okay, once you have a formal parameterization of the black curve, you start with a V0, and then if you go around this closed loop, you see that when you come back, it has rotated by 90 degrees clockwise. It's not the same vector V0 anymore. Okay? That already tells you that the torus cannot be, I mean, this torus cannot be flat, because if it were flat, then this loop joining P to P, whatever parallel transport you get should be the same as the constant loop joining P to P, for which the parallel transport is identity. But this is clearly not identity, so this torus is not flat. Okay. Any questions or comments before I go on to the second example?
Sir, can you explain what did you say about the bottom black line?
Yes. So what I said is, if you look at the bottom black line, take any point here. What is the tangent space at that point? The tangent space at that point is going to be a sheet of paper which is touching exactly at that point, right? So just consider, let's say, the extreme point here. So what would that be? That would be a plane which contains a vertical line, and then it also has another. So if I take any point on the bottom black circle, the tangent plane to the torus at that point is going to be a vertical plane. But that means all of these red vectors, these are vertical vectors, meaning they look like 0, 0 something. They are always in the corresponding tangent spaces. So when I simply parallel transport this red vector in R3, which means I don't do anything at all, and then when I project it back, I don't lose anything because these vectors are already part of those tangent spaces because they're vertical, and the tangent space at any point of these, any point on the black circle is a vertical plane. So remember, the point is when I parallel transport, how do I parallel transport something in a submanifold? I have to parallel transport their extended vector fields and then project it down to the tangent space. So when I project things down to the tangent space, I might lose things. So here, for example, the projection will happen in a non-trivial fashion on this segment, the third segment. So the first segment, we didn't see anything because the projection was faithful. The second segment, we didn't see anything because the projection was faithful. On the third segment, we are going to actually have to work this out, how the projection works, because this is not the constant vector field, right? However, on the last segment, this is again the constant vector field because these vertical vectors are part of the tangent spaces at the corresponding points, because the corresponding tangent spaces are vertical planes. That's just something you have to write down. I mean, if you have a point on the equator, calculate the tangent space, you'll see that it has a z-axis in it, and these vectors are living on the z-axis. Is that okay?
Yes, sir.
So just try to, I guess, this is the picture, but as I said, you have to write down the explicit curve. It will be 1, 2, 3, 4, and then do the parallel translate in each of the 4 segments, and then if you get stuck, we can discuss this again. But the picture should be the guiding light for what you want to prove. That when you come back, it should rotate by a certain angle. In this case, 90 degrees. Okay.
Sir, here orientation is the important thing, because if we do in the opposite, in the same path in opposite way, then the vector remains.
Sure, orientation is important, but the point is, see, oriented or not, you are saying that there is a loop, so that when I parallel transport along that loop, it's non-identity, right?
Yes.
So that already tells me that this surface cannot be flat, because I already know that the constant loop has identity parallel transport because I don't do anything. And although this loop is homotopic to the constant loop, this is not a topological phenomenon. That is what I want to highlight. This loop is clearly contractible, right? You can just make it shorter and shorter. So being homotopic is not really the issue here. This is homotopic to the constant loop, but the constant loop acts by identity and this acts by rotation by 90. And there's no contradiction here because rotation by 90 can be gradually unrotated to rotation by 0, which is identity. So everything is okay. It's just that being homotopic is not the issue here. The issue is whether parallel transport, non-triviality of parallel transport detects the curvature, and in this case it does. Okay, any other questions? All right, so let's move on to the next example then. The next example is something I had talked about once. Let me talk about it again. The parallel transport on the unit sphere. Okay. So you consider a geodesic triangle with internal angles pi over 2. Such a triangle is not possible on the Euclidean plane for obvious curvature reasons. Such a triangle is possible on the sphere. Okay. So this is a geodesic triangle, meaning that these are part of great circles. So this one is the equator. This is a great circle, part of a great circle. These angles are 90. Okay, this is 90, this is 90, this is 90. Is that clear? So what we want to do is we want to parallel transport some vector starting here, going up, going here and coming back. And again, we'll see that this is not going to be identity. So I hope the loop is clear. The loop is going to be something with angles 90, 90, 90. So for instance, you can take this to be 1, 0, 0. You have to move up an angle pi by 2, and then you move up to the north pole, and then you come down. So you can write down an easy parameterization. So yeah, so let's start with V0. This is the origin. So that subtends an angle 90 here. This is 1, 0, 0. This is like 0, 1, 0, for example. And this is 0, 0, 1. So we want to parallel transport this V0 along this blue segment. What should happen? Remember that this blue segment is a geodesic, right? So if I parallel transport a vector along a geodesic, we saw that parallel transporting a vector along a geodesic, this vector, the angles and the lengths are going to be preserved as I parallel transport this along a geodesic because of metric compatibility, right? Which means this is what I get. At every point I get a V0, which makes an angle 90 degree with the with the curve, the blue curve at the corresponding point, and the length is the same. So if this has length half, this will also have length half. It will still make an angle 90 degree. But the two blue arcs already had an angle 90 degree here, which means this red curve is going to be a tangent to this blue curve, correct? Because this internal angle was 90, and the angle between this red vector and this blue curve is 90 because that was the initial angle, and angles are preserved when I parallel transport along a geodesic. So this red curve is a tangent to this blue curve. But this blue curve is a geodesic. If I parallel transport, it's simply going to be its velocity, right? Up to a scaling. So at the end, when I end up here, remember this is 90. This is going to point down. This is simply going to be a vertical vector pointing down. Is it okay so far? So now what's the rest of the story? Well, now you parallel transport this vertical vector back along this part of the equator. But what should happen? The equator is also, all of these are geodesics. The equator is also a geodesic. So if I parallel transport this vector back, it has to have the same length at every point. It also has to maintain its perpendicular orthogonality along with the equator, which means it looks like this. It's the same vertical, it's the same picture as the torus example, pretty much, right? But what do you see? You see that you start off with this horizontal vector. When you come back, it has rotated by 90 in this case. And it's actually easier to explain why 90 in this case, although I'll not be able to give you the details immediately. The reason why it's rotated by 90 is because of a key fact that, remember, you have this triangle, right? What are the internal angles? 90, 90, 90, right? So what is the area of this triangle? Does anybody know what the area of this triangle is? I mean, just from
One eighth
Is
of the
half pi square.
half pi squared. Why?
one eighth of the area of the
Yeah, so what is the
sphere.
surface area
It's
of,
half pi.
yeah, so it's pi over 2,
Because-
right? It's 1/8 of 4 pi, correct?
Yeah.
Because you just break it up into 4 slices on the top, 4 on the bottom. They're all equal.
Yeah.
So it's 1/8 of 4 pi r square. R is 1, so it's pi over 2. So this has surface area pi over 2. Okay? However, this is not pi over 2 by accident. This is pi over 2 also because if you take the sum of the 3 internal angles, how much is it? It's 3 pi by 2, right? And then you subtract off pi. Why are you subtracting off pi? Because remember that if you take the sum of the 3 internal angles in a Euclidean triangle, you subtract off pi, you get 0, right? So you cannot say anything about the area of a Euclidean triangle by knowing the internal angles. The area could be arbitrarily large, arbitrarily small because of dilation, right? So if I take a Euclidean triangle of angles alpha, beta, gamma, the sum is equal to pi. I could dilate them to still have internal angles alpha, beta, gamma, but the area could be arbitrarily large, right? So the angles do not determine the area because the Euclidean triangles are in curvature 0 setting. However, in other curvatures, the angles do say a lot about the area. So in particular for the sphere, we have seen that this has constant curvature 1, Gaussian curvature 1, right? So if you calculate the area of the sphere, this will turn out to be the sum of the internal angles minus pi, which is the excess of the internal angles. So the excess of the internal angles here is exactly pi over 2 because it's pi over 2 plus pi over 2 plus pi over 2 minus pi, which is pi over 2, right? So it's pi over 2 from both calculations. So the area of this is pi over 2. And the reason why this rotates by pi over 2 is exactly because of the area being pi over 2, because there is a relationship between the curvature and this phenomena called holonomy, that if you go around a certain loop and come back, the initial vector might rotate by a certain angle, and that has a lot to do with the curvature. And the curvature can, in this case, be integrated along the region which the loop traces. And that exactly corresponds to the rotation in a certain sense. Yeah. So in any case, so it's rotation by pi over 2 again because of this specific choice. So this is also an example that all of you should be able to explicitly write down and check. Okay. So any questions? Okay. Okay, good. So this again tells you something which we knew all along, that the sphere is not flat, or that the Earth is not flat. So all right. So let's move on to something slightly more interesting. Well, I mean, this was interesting as well, but something more interesting from the point of view of other things that we're going to study. So you want to expand the Riemannian metric in local coordinates. It's a very natural thing to do because you are talking about first, second, and higher order derivatives of the Riemannian metric. So you might as well choose nice coordinates where the metric looks easy to work with. In general, if you say I choose arbitrary local coordinates and the metric is just Gij, and then you don't know what the derivatives of Gij's are apart from computing. So it makes natural sense to look for local coordinates such that the second order Taylor expansion of the metric is as simplified as possible. Okay? Yeah, so there's a typo. There should be an I here, simplified. Okay, so what do we mean by this? Well, let's start off with a normal neighborhood, because normal neighborhoods are nice, geometrically motivated. So U, I'm going to call U as BRP, but it's really going to be the image of a ball. This is a normal neighborhood. Okay, so normal neighborhood means what? It means U is really the image of some appropriate ball around the origin in TPM, and the exponential map restricted to that ball is a homeomorphism from that ball to U. And the normal coordinates are the coordinates coming from TPM, which has a natural coordinate x1, x2 up to xn, because TPM can be identified with Rn. Okay. Yeah. So in the normal neighborhood, what happens is that for any q in U, q is the image of some exponential of some vector v coming from TPM. So you can always pretend that q is going to be the p-image. I mean, the p-image of q is a vector v in TPM, and the p-image of p is the zero vector in TPM. And if you join the radial line from 0 to v, the image under the exponential map is the geodesic gamma q. And I'm calling it normalized because my geodesics are always unit speed. Okay, so normalized means unit speed. So the unique geodesic joining p to q, I'm calling it gamma q. And this is nothing but the exponential of the line segment, the radial line segment joining 0 to v, where exponential v is q. Is that all right? Okay. So it's just a brief recall of what normal neighborhoods are. Okay. Yeah, so this geodesic corresponds to a radial line joining 0 to the vector exponential inverse of q. Okay. So now choose an orthonormal basis E1 through En of TPM. And what can you do? So if you like parallel transports, and there's no reason to not like it, what you could do is you could start off with E1 into En. So these are tangent vectors. These are orthonormal bases at TPM, correct? So now you can parallel transport Ej along gamma q. So see E1, E2, En, these are orthonormal bases at TPM. But now you can just take the geodesic gamma q, which is simply the image under the exponential map of the radial line segment joining 0 to v, where v goes to q. And you just parallel transport these E1 through Ej's along gamma q, which defines vector fields Ej. So we have vector fields E1, E2, En. So that E1 at q is simply going to be the parallel translate of the little vector Ej along the geodesic gamma q. This is the definition of Ej is clear. So it exists by parallel transport and so on. So what you have to show is that EIs are smooth vector fields and they're orthonormal at each point. Orthonormality is again going to follow from metric compatibility and your parallel transporting along geodesic. It's just that fact. Okay, that EIQ dot EJQ is 0 because they're parallel transports of EI and EJ, and EI and EJ are themselves 0 at the point P. and dot product. Okay? So these are smooth vector fields which are nice in the sense that they are orthonormal at every point Q and they're defined at every point Q. So you get an orthonormal family of vector fields at all points on U, which is very nice. Okay. So you might ask, okay, if these are nice vector fields, what can we do with them? Well, can I talk about the covariant derivative of EI with respect to EJ? Is it 0? Okay. So again, I'll just skip through this a little bit, but the exercise that you have to show is that indeed that is true. If I covariantly differentiate EJ along EI, that is also going to be 0. Okay. Almost by construction. Okay. So you can read through this last bit because I want to get to something which is more fundamental. So I mean, such a thing is nice because it gives you what's called a geodesic frame, meaning that you get an orthonormal basis from the restriction of the vector fields to any point in U, and this orthonormal basis has the property that the corresponding vector fields, when I calculate the covariant derivative, they're 0. Okay? So such a U1, E2, En is called a geodesic frame, and it's useful in a lot of computations in geometry. But the real question that we should ask is, these vector fields are fine, but are these vector fields really coordinate vector fields? Is there some coordinates x1, x2, xn such that Ej is d by dxj? That would be even nicer, right? Because then that would say that these d by dxi's are perpendicular. Nabla d by dxi with d by dxj is 0, and this happens all over U. So that is very, very nice, correct? So what do you think? Is it possible that these EJs in general can come from some d by dxj's such that d by dxi dot d by dxj is delta ij, and then nabla d by dxi d by dxj is 0?
So for a flat surface, that's flat manifold, that is possible.
Yeah, okay, good. So now that you said this, yeah, so for flat, of course, things are different, but if you didn't know anything about M, you cannot expect this to be, I mean, you can get these EIs, and the point of this slide is that's the best you can do. You cannot expect the EIs to be d by dxi's, because if there were d by dxi's which were orthonormal all over U, that would mean that the GIJs were delta IJs, right? So that would mean that the Riemannian metric on U looks like the standard Euclidean metric. So that would mean that U with the metric G is isometric to some ball in Rn with the Euclidean metric. So that would mean that that piece of the manifold U is actually flat. Right? So you cannot expect EIs to be arising from coordinate vector fields in general. Ensuring that this first exercise holds true, that they're orthonormal over all points. They can be orthonormal at a point, but not over a whole open set. Okay? But that is our goal. Our goal is to, so we cannot look for an orthonormal family of coordinate vector fields, but we can look for something weaker, and that's what we're going to focus on. Okay. Are there any questions before I move on? So I would highly encourage all of you to read through this slide just so that you are aware of this construction called a geodesic frame. We may not make much use of this later on, but I wanted to put it out there because this is an important construction. Okay? And since we have talked so much about parallel transport, this doesn't take much work. Okay, so let me move on. So yeah, so let's get back to the exponential map. So the exponential map is a local diffeomorphism. We have proved this. So any element Q in U can be expressed uniquely as exponential of x1 e1 dot, 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 up to xn en, where EIs, remember, was a chosen orthonormal basis of TPM. So you fix a choice once and for all, e1 through en, which is an orthonormal basis of TPM. And so the xi's are going to be the local coordinates around P, because every Q in U can be written in terms of a unique such n tuple, right? Okay, so what is our Gij? Well, our Gij at x is nothing but Gij of x1, x2, xn. But what is this? Remember, this is nothing but you take the vector field del by del xi, apply the linearized exponential map, take the del by del xj, apply the linearized exponential map, and then evaluate this at the point Q. So this inner product is happening in M using the Riemannian metric G. That's what this Gij is, right? So essentially what I'm doing is I'm pulling back the metric on M to TPM via the exponential map so that we can calculate everything on U. All right. So what happens? So you have to calculate this. You can show that if I evaluate this at 0, 0, 0, it's no wonder that Gij at 0 is delta Ij. So at the point P or at the point 0 in the local chart, the Riemannian metric, the associated matrix is the identity matrix. And the Christoffel symbols only at the point 0. Remember 0 here corresponds to 0, 0, 0. But that corresponds to exponential 0, which is the point P. So when I write 0 here, I'm working in TPM. When I'm writing exponential of certain things, this is happening in the image of the exponential map, which is in M. So this is a simple exercise. Show that with the normal coordinates, at the point 0, the matrix is identity, and the Christoffel symbols are also 0, but this is only at the point identity. Okay. So what can we do? Well, we can use what the Christoffel symbols are, and let me recall you what they are. This is half the inverse of the matrix G, and then there are some derivatives. So this means del by del J of GMI. This is del by del I of GMJ, and this is del by del M of GIJ. Okay. So what we could do is we could evaluate this at x equal to 0. And what we get if we evaluate this at x equal to 0, well, we get the right hand side is, the left hand side is 0 because of the previous formula. And G is invertible. So what we get is that this, the three terms here, they add up to 0 for any I, J, and K. Okay. Is that okay? So the red line is an exercise that you can calculate. It's a one-line calculation, but then using the computational definition of the Christoffel symbols, you can conclude that G satisfies this identity. That GKI differentiated along J evaluated at 0, GKJ evaluated along Xi at 0 is equal to GIJ differentiated along K evaluated at 0. Okay. So what can we do with this? Well,
Sir, sorry, my phone was not silent.
That's okay. I mean, as long as I don't think it created any disturbance. Yeah, so once you have something like this, now it's a matter of simple algebra that if you add three of these things by cyclically permuting, you can conclude that Gij is 0. But this is only at the point 0, okay? So this is saying you take del by del xk of Gij evaluated at the point 0, this will be 0. You just have to add three such equations in some cyclic order, and then you'll have, you'll get what you want. So anyway, having this, it tells us what? It tells us that if I want to expand Gij in the Taylor series, there is already Gij at 0. By the exercise, this is the identity matrix or delta Ij. Then there are no linear terms because all the first order derivatives of Gij at the point 0 are 0 by this second exercise. So I only expect second order terms, right? And that's exactly what we're looking for. But are the second order terms entirely arbitrary or they are very specialized? That's the question you should ask. And that's the question, in fact, Riemann had asked. And it was his genius that he could combine certain things and come up with a formulation which, I mean, it's hard to guess how he came up with it, but, you know, for simple reasons that it's hard to sort of quantify how a genius would think. But there are reasons why he came up with the formula that is now called the Riemann curvature tensor, and I'll make some comments when we get there. Okay? So we want to expand Gij, and then we see that it has delta Ij, and then there's no linear term, and then we are interested in the second order term. Okay? So the Taylor expansion is given by something like this. Okay? So it's delta Ij plus this notation means that I take the del by del xk del by del xl derivative of Gij at the point 0, and this is the usual Taylor expansion, x to the k, x to the l divided by 2, and then there are higher order terms, right? So this is exactly the Taylor expansion up to order 2. Is that okay with everyone? All right, good. So what did Riemann do? Let's get into the heart of the matter. Okay. So in what follows, we are going to very much follow Spivak, and I've given the reference at in the footnote. It's volume 2, chapter 4, almost from the beginning, but you can skip the first few pages if you want. So I would highly, again, I mean, I cannot emphasize this more. I would highly encourage everybody to read the relevant parts of chapter 4 because it's very, very well written. There is a bit of a computation which I'll not do, but if you read Spivak, it's pretty clearly written what the computations are. And to my sort of surprise, very few books in Riemannian or differential geometry actually treat this fundamental formula of Riemann the way it should be treated to do any justice. They usually put it as an exercise like in Peterson's book, or it's referred to in passing without any mention of how this is done. Okay? And it can be done using a more sophisticated machinery called Jacobi fields, and that is how it's done in some other books. But it can also be done in a more elementary fashion, like it's done in Spivak. It can be done in an even more elementary fashion, like how Riemann did. So, but we are going to follow Spivak because can everybody hear me? I think the internet was.
There was a lapse in the audio for 3-4 seconds.
Oh, so yeah, so I'm just saying that there are 3 ways one can go about proving this famous formula of Riemann. Most books don't have a good discussion on this. So Spivak has a complete discussion, but it's kind of elementary. There's the Riemann's original approach was even more elementary, but then you have to really count certain things in a certain way. But it is indeed a very low machinery approach, and the usual slick approach is through Jacobi fields, which we'll not talk about, but some books use that to prove this formula. Okay? Anyway, so there are so we are going to follow Spivak. Okay? So what we do, well, if you expand the Riemannian metric, so the Riemannian metric is a 0-2 tensor because it takes in 2 vector fields and outputs a scalar or a function. So then we know that the Riemannian metric can be, if you take the norm square, what does it look like? It looks like Gij at x, dxi, dxj, right? It's a symmetric 0-2 tensor. So it feeds in 2 vectors v, w, and it outputs a scalar. So this is the Riemannian metric, correct? Gij, dxi, dxj, but this is not dxi wedge dxj. This is dxi tensor dxj. And because Gij is gji, this is symmetric. Okay. So make sure you note it down because this is not a 2 form; it's a 0-2 tensor. So if I expand this, remember Gij was delta ij plus some higher order terms. So because it's delta ij, the only time I'm going to have anything survive is if I is equal to j. So that's a dxi tensor dxi. Correct? This is basically this. I'm just applying this last line to this. Okay, and then you will have this term, right? Plus higher order term. So I'm writing order of norm x cube. Spivak writes order of norm x square. The reason being, I'm pretending this is higher order terms from order 2, so it has third order. The reason why Spivak writes mod x to the 2 is that in any case we both mean the same thing, is that whatever terms appear here, if you divide by mod x square and take a limit as x goes to 0, this will go to 0. That's what I mean by higher order terms, and that's exactly what Spivak means as well. But the notation is different. So I'm mentioning this because when you read Spivak, there shouldn't be any confusion. This simply means that whatever terms appear here divided by mod x square, limit mod x goes to 0, all these terms go to 0. Okay. So this is what we get, but let us denote this quantity by Cijkl. But there's a comma. Okay. Cij for the Gij, the comma is the comma, and the kl are the derivatives, so the kl comes separate. So we know that these satisfy certain properties. Well, what are the obvious properties? If I switch I and j, nothing changes because G is symmetric. If I switch K and L, nothing changes because G is C2. So the partials, the second order partials commute. So this clearly satisfy these identities, right? Okay. Riemann's main assertion is that there are numbers capital C, I, J, comma, KL, such that you can write it in this form. So this is only for the order 2 terms. You can write this expression, which is the order 2 expression over here, in this specific form. Why in this specific form we will get to in the subsequent lectures. But if you remember what we talked about in the curvature 2 form and the curvature matrix, this should remind you of something similar. Okay? So why he thought this form was relevant is because it is connected to the curvature matrix for surfaces. But nonetheless, he wanted to claim that there are numbers Cij, Kl such that this expression can be written in this form. And this is not a trivial matter entirely, because this form is a very specific kind of a rearrangement, right? It's not clear if I give you a bunch ofCijs just having these properties, it's not clear whether you can solve for this capitalCijs, right? So this requires some insight as to how you can do this. Why you want to do this is again motivated from the curvature matrix. Okay, so he asserted that there are these numbers. So how do you go about proving this? So before I move on to the actual sketch of the proof, are there any questions? Okay, so let's see.
So we actually saw that earlier that the Riemann curvature tensors components are basically dependent on the second order derivatives of the metric
Yes, yes, exactly.
and the connection coefficients. It comes to cross products and
Yeah.
such things. So can we perhaps expect that if the curvature is in some sense simple, then the third order expansion terms disappear in this expansion or something like that?
Well, the third order expansions are going to be there, but the point is they're not going to disappear. But I'll maybe you can ask me this question when we get to the last slide, because I'm going to address something that might answer part of your question. Okay, so we are going to see the Riemann curvature Rijkl appear. Okay? But the reason why I'm not, I didn't want to say it right now is that if we, like pretend that you are in Riemann shoes for once, and if you are trying to develop this, you didn't know that there were these things called Rijkl, and even if there were, as you will see, there's a lot of choices involved. So at some point, you have to choose a convention and say that this is my Rijkl.
Okay.
And so which one do you choose? Like we have already seen certain conventions in contracting and sort of notation already. So I'm going at this along the historical sort of route, so to speak. Okay, but yeah, just like hold your thought for a minute. Hopefully, it will get answered in subsequent slides. So yeah, so this is something that we want. This capital Cijs motivated from the curvature matrix from surfaces. So now, if you follow Spivak's book, and again, I highly encourage you to do that, there are two parts to the proof. Okay, there's a purely algebraic part, and this is nice, but it's a bit of algebra. But if you like algebra, I mean, I found it very nice. It's an algebraic fact about quadratic functions. It says that these capital Cijkl exist if and only if the little Cijs satisfy some symmetries. One of the symmetries is this, that Cij, Kl is Ckl, Ij. So this is new. We didn't know that this is true, right? The only symmetries that you could deduce is that Cijkl is Cjikl, or you can switch K and L, switch I and J. But switching Kl entirely over Ij, that we don't know. But this should remind you of vaguely of one property of the Riemann curvature tensor, right? The Riemann curvature tensor had a similar property. You can switch over the entire last pair over the first two pairs, correct? Okay. Then there's this other property, which again should remind you of something, right? What should this remind you of?
Bianchi identity.
Remind you of
Bianchi identity.
somehow this is like, like the comma is separating the first two and the last two. So it's very tempting to say that, oh, so maybe these little Cijkls are my Rijkls. As you'll see, that is not the case. Okay, so there's a lot of choices regarding what you might want to call curvature. Even if you are very tempted, you call this the curvature. This would not be the curvature simply because this is not going to give you the Gaussian curvature. Okay? So there's a choice that Riemann had to make. It was necessary. So anyway, so the algebraic claim is that these capital Cij exist if and only if these two properties hold true. Moreover, in this case, the capital Cij is nothing but 1/3 of the little Cij. Okay, so that's an algebraic proposition, if you wish. So this is nothing to do with how the Cij arise. It could be just anything. This has nothing to do with the Riemannian metric whatsoever. It just is answering this last algebraic question. Okay. So now let's come back to the analytic part. So the analytic part would mean that you have to actually show that with the normal coordinates, the Gij satisfy these two equations, because otherwise you cannot get hold of this capital C. You have to show that these two equations hold. Okay? And that's a fair bit of computation. It's a couple of pages. It's not too hard, but it is a couple of pages of computation. Okay, so but one of the key step involves showing that if you take the matrix Gij, the entries Gij of the matrix G at the point X and multiply with X to the J and sum over J, then what you get is X to the K. Okay, so this is something which can be shown without much effort, but this is one of the steps. You have to do a lot of steps after this, a couple more. But I just outlined this because if some of you go back and read Spivak, this is one of the first things it proves. Okay? So it's considerably harder and it uses this as a stepping stone. But you have to establish that for the Cij KLs, which is half of Gij comma KL, both these identities are satisfied. Okay, so it has two parts, and I'd leave it here. You can go back and read from Spivak. Okay, so what does it give us? So are there any questions so far regarding the structure of the proof? So you separate the question into two parts and then you just solve them, each having a different flavor. Okay, so if you compute further using the analytic step, you can in fact show that this Cij KL, which is nothing but half of Gij differentiated along KL direction at 0, is minus 1/6 of Rikjl, Riljk. So here the indices are crucial. I and J appear in the first and the third place. K and L appear in second and fourth and second respectively. Okay, it's not IJKL, it's I something, J something, and the somethings interchange. Okay, so this is again a small computation, but if you follow the proof from Spivak, this is just a simple one-line deduction from there. So as tempting as it was to callCijkl as Rijkl, you see now thatCijkl is not Rijkl, at least not the modern Rijkl, it's something else. Okay. Okay, so if I plug this back in, I get this famous formula of Riemann, which says Gij at a point X. If I Taylor expand, I'm going to get delta Ij. There's a minus 1/3 because there was a half and the half. Remember, Cij already has a half. And the half is going to cancel and the minus sign stays. So I get a minus 1/3. And then because I have these sums over here, I can put 1/3 IKJL here and 1/3 IKLJ there because the XKXL takes care of the symmetry. So, and then there's order 3 terms and higher. Okay, so this is what we get. So I'll give you a moment to just look at this formula and then I'll make some remarks. This is a very, very beautiful formula. I mean, if you're seeing this for the first time, when I saw this for the first time, I was quite blown away with it because I knew a little bit of differential geometry and so on, but nobody had told me that this was something that you can expect in a specific coordinates. And if you write it down in the normal coordinates, which is geometrically very, very natural, then there is no there is no first order term, and then the second order term, the coefficients that appear are precisely the Riemann curvature coefficients up to the ordering, which has to be precisely in this form. It's not Rijkl, but it's IKJL. Okay. So this is nice. It says that if you expand the Riemannian metric, it's identity plus some second order stuff. second order captures the curvature, and then there are higher order terms. And one can say a lot more about what higher order terms and so on. We will make those remarks next time. But for now, you note that if your manifold was flat, then you know that Rikjl is 0 for every point. So one thing to note here, it's a small typo. When I say Rikjl, this is at the point 0. Same here, this is at the point 0 in the line above. Okay, this is not Rijkl at x, obviously, because Taylor expansion means the coefficients are things evaluated at the point 0. So this is like Gij at the point 0, that is del ij. Right? This is the Riemann curvature coefficients at the point 0. Okay. So if the manifold was flat, then that would mean that it is 0 up to the second order. But in fact, if you work out the third order terms and so on, you can show that in fact all of those are also going to be 0 if Rijkl was 0 in a neighborhood, because they will involve higher derivatives of these tensors and so on. Okay, any questions on this? So this is not a complete deduction, but modulo the two main steps from Spivak, this is a deduction modulo then. But I just couldn't help but share this in the lecture, because this is not there in DOCARMO, at least as I want it to be explained. And although this is not part of the formal syllabus, I mean, it would be an incomplete course if you haven't seen this. It's such a beautiful formula. Okay? So yeah, so now coming back to this remark, so Riemann had to make a choice. What do you call Rijkl? Because you can expand this in lots of different ways, right? Rearrange them and call something else Rijkl. His choice was motivated by two things: that whatever you call Rijkl has to transform properly, meaning if I choose another chart and do things, it transforms equivariantly. It transforms as a tensor, and it has to agree with the Gaussian curvature when I restrict to the case of surfaces, and hence this choice. Okay, because as we saw, Rij if normalized is the Gaussian curvature. Okay. Okay. So any questions? So we'll do one last example and then we'll stop. Okay. So I mean, I would highly recommend people to read those few pages, 5-6 pages of Spivak, because it's very nice. This is not for any coordinate, mind you. This is not saying you just take any local coordinates, expand, you're going to get this. No, this is for normal coordinates, that the first non-trivial term that shows up in the Taylor expansion are up to a factor of -1/3, the Riemann coefficients. Okay, so let me then go on to the example. So we'll choose an example where we already know the answer. So the sphere of radius r. So what is the Gaussian curvature of a sphere of radius r? So this you should have done in curves and surfaces, right?
1 by r or something like that.
No, 1 by r is, see, I mean, each curve on the sphere of radius r has curvature 1 by r, but Gaussian curvature is a product, so it's 1 over r square. Because all the principal curvatures are the same, they're all 1 over r.
Yeah.
So usually the Gaussian curvature is you take the maximum, the two extremum of the curvatures, the product is the Gaussian, and up to a sign, the mean is the mean curvature, right? So here everything is 1 over r, so the Gaussian curvature is 1 over r square, and the mean curvature is 1 over 2r with a plus or minus sign, depending on whether it's normal pointing outward or inward. So we know that. Now let's consider this sphere. So this is S2r. The r stands for the radius. This is induced with the Euclidean metric. What are the geodesics? Well, the geodesics are great circles. And as you all know, this is a geodesic initialized at P. So we're going to choose P to be the north pole, which is 0, 0, r. But this works for any P. Okay, so geodesic initialized at P are given by this curve, which is a cosine and sine functions of P and a vector V. So V is going to be a tangent vector at P. That means V is perpendicular to P. And because this is happening on a sphere of radius r, I have to recalibrate V by multiplying V over norm V with r. Otherwise, this would have norm 1. I want this to be norm r, so that when I take p cosine something plus this times sine this into sine of something, when I square and add, this is going to be of length r square. But I mean, all of you have seen this already. So this is a great circle and hence a geodesic. Okay? So if I want to calculate the exponential map at the north pole, what do I want? I want to evaluate this gamma at t equal to 1, where p is 0, 0, r, and v is going to be a vector perpendicular to 0, 0, r, which means v looks like a, b, 0, right? Good. So let's take the standard vector fields E1, E2 at the tangent space of S2 at the north pole. So E1, E2 looks like 1, 0, 0, E2 looks like 0, 1, 0, and these are tangent vectors at the north pole because 1, 0, 0 and 0, 1, 0 are perpendicular to 0, 0, r. Good. So any questions on this basic setup? Okay. So what do you want? Well, you want to calculate. So what do you want? You want to calculate this d of the exponential map, because at the end of the day, you want to pull back the metric on the sphere to TP of S2R and calculate everything there. You want to make this calculation happen in R2, right? That's what we did. So this is an exercise, and it looks like a lot of terms, but it's not. It's a simple matter of bookkeeping. You just have to, because I've given you the formula, it's even easier for you to verify this. So if I take the exponential map, take the linearization of the exponential map at V. So V, remember, is an element of TP S2, where P is the north pole. So if exponential map is defined on all of TP, on all of the tangent space, because the great circles are defined for all times. If I linearize the exponential map at V, evaluate it at E1, this thing is going to read V1, there's a E1 here, there's a V1 here, and this is going to be V2. Okay? If I evaluate this at E2, this is going to be V2, E2, V2, and this is going to become V1, because whenever I have something like 2 plus 1 is 3, I read mod 2. So 3 mod 2 is 1. So this expression works for E1 and E2, for both. I've just written it in the condensed form. Okay. So is the expression okay? I mean, not why you get this. This is something you can go back and check. I'll not bother you with the computation because you've already seen enough computations. But so this is going to say that if I wanted to calculate the metric on the R2, which is the tangent space at P of S2, by pulling back the metric, I have to first know what these vectors are, right? And this is what these vectors are. So what do I do now? Well, so there's actually one more term. Yeah, sorry, I skipped it. So for E1, this is going to have a E1 term and a E2 term and a P. So it's going to be a combination of P, E1 and E2. Similarly, if you put E2 here, it's going to be a combination of P, E2 and E1. Okay? That is expected because a typical vector in S2 is going to be a combination of 3 basis vectors, P, E1 and E2. Right? Okay. So if I now compute, this is really the hard part. If I now compute the inner product of this vector with itself or this vector with E2, I basically get my matrix Gij, right? So Gij at V is going to be d exponential V of E1 dotted with itself. G12 is going to be d exponential V of E1 dotted with d exponential V of E2. G22 is going to be d exponential V of E2 dotted with d exponential V of E2. So this is, once you have this, it's a matter of just computing, and the fact that E1 dot E2 is 0, E2 dot E2 is 1, E1 dot P is 0, E2 dot P is 0, P dot E2 is 0, and so on. Okay? So you have all these P, E1, E2 forms an orthonormal basis. So the computation is easier, but you have to know what this thing looks like. Okay? So standard computation will show you that the matrix G at the point V looks like this, okay? Where V is of the form V1, V2. So is this all right so far? Okay, so now it's time to expand this, and you will see why the calculation is very important, because whatever you calculate here, if there's anything wrong somewhere, something will go wrong here, and if something goes wrong here, the expansion will detect that error and in turn the Riemann curvature is going to turn out to be something other than 1 over r square, and it has to be 1 over r square because it's a surface, we know everything about it. So this is this again modulo order 3 terms. This is not the whole thing, of course, but this is the first, the constant, the linear, and the second order terms. Anything else which has a v2 cube or v1 square, v2, all those terms are deleted from this expression. I only care about the matrix up to order 2. So yeah, so prove the above claim, meaning that you just show that G11 is this, G12 is this, because it's symmetric. You only have to compute 3 things: G11, G12, G21. Okay. But if you expand this, what do you get? So let's expand this. This is already 1 minus something, 0 plus something, 0 plus something, 1 minus something. So this already is of the form identity plus no linear terms. And then the quadratic terms look like minus v2 square over 3r square, v1 v2 over 3r square, v1 v2 over 3r square, minus v1 square over 3r square. So it's also important that v2 appears in the 1/1th place and v1 square appears in the 2/2th place. And you'll see it couldn't have been otherwise. Okay? So let's look at G11. What is G11? It is 1 minus v2 square over 3r square. But if you go back to our notation, what is v2 square? V2 square is like x, x square, x2 times x2. So it's v2 into v2. So then the corresponding coefficient that should appear from the formula of Riemann, forget this fact, just imagine the formula of Riemann. It should be 1 minus 1/3 r of 1, 2, 1, 2, v2, 2, because we're expanding G11, I is 1, J is 1. And the only term that survives in G11 is v2 square, which is v22. So the coefficient that should appear in front is r12, r12. Is that clear? Just think about it for a minute and go back to the notation here in the formula. This appears like this. In the expansion of Gij, it's rikjl, and what appears here is xkxl up to a minus 1/3. So I'm saying, so this is what Riemann tells you, right? But if I compare with what we have, what do we get? We get r1212 is it is 1 over r square, right? Is that okay with everyone? If you want, I
Yes,
can
sir.
go over that again. So I'm saying, think of the formula of Riemann. It says you expand G11 in Taylor series. It's 1 minus, there's no linear term, 1/3 r1212 v22 plus there will be other terms. But we see in our expansion that the only term that appears is v2 square, which means this is the only term that survives according to the formula of Riemann. But on the other hand, we know that in our computation, we get v2 square up to minus 1/3 into 1 over r square. So if I compare the two, I get r1212 is 1 over r square, which is the Gaussian curvature. And that is because this E1, E2 is an orthonormal basis at P. So we don't have to normalize. Okay, it is 1, 0, 0, 1. Similarly, if you expand this G12, what happens? G12 expansion, you have this term V1, V2, right? So that means you're looking at R1, V1 to XKXL. So V2, yeah, so okay, so I guess one has to be careful. So when you look at V1, V2, you have to think of it as V2, V1. So when you expand the G12 term, you'll get R1221, and you get R1221 is minus 1 over r square because there's no minus sign here, but R1221 is minus R1212. So that's what you get. So you recover all the Riemann curvatures as one single element, R1212. Everything is up to a multiple of sine plus minus 1, R121. So these things are very precise. You have to have V2 square here with a minus sign. You have to have V1, V2 with a plus sign. You have to have symmetry, and then you have to have minus V1 square. It cannot be anything else. So in other words, we are recovering the fact that there's only one non-trivial Riemann coefficient for a surface up to a sign, which is R1212, and that is the Gaussian curvature of the sphere of radius r. So are there any questions on this? And this is a simple example, but I hope it highlights the formula and what we need to compute, even for a simple example. Okay, any remarks? Okay, so yes, as I mentioned in the email, it would have helped if you did some of these computations. If you haven't, that's no worry. You can go back and read this example. This is a simple example, can be done several ways, but hopefully it highlights and brings into picture how you could have computed this just from the formalism of Riemann. So next time we're going to talks a little bit more about flatness, the converse to the parallel transport independent of curve implies flatness, and talk a little bit about sectional curvature, and hopefully we'll see from there what to do. So I do want to talk a little bit about Ricci curvature at some point, but I do want to focus on sectional curvature first, because that is in some sense more important, at least from the perspective of the course. So if there are no more questions, let's stop here.
Sir, how long will the, so it's a general question, how long will the online classes go on?
Oh, so for my thing, see, I'm planning to take another 3 lectures to cover sectional curvature, Ricci curvature, and then highlight what are some big theorems and open questions and so on, and then we'll be done. So if people are interested, I can take a tutorial or a problem session sometime in the first week of June, if enough people are interested. Otherwise, it will be basically, I think, 3 more classes.
And in general, has there been any unofficial discussion regarding how long shall the online classes go? Like when shall the syllabus be completed?
No, that
Like in all courses?